grabbed a lot of stuff out of existing documentation that's out there. There's so much of it that it was pretty easy to get what I needed, but it just took a while to find the bits you want. You can't put this stuff together unless these guys do their stuff. Flim IO boards of Ian's, I like them a lot. Craig's mileage varies apparently, because I actually like that they've got all the options on there because they make them quite flexible. You just have to wrap your head around what they're doing. And this board will do all that the CAN MIO servo board will do and the CAN MIO add will do. This one here is actually built as a CAN VOUT, but by adding extra regulators and changing its configuration slightly, you get the equivalent of that CAN MIO servo board. Let's have a look. This one is configured as CAN VOUT. This one I think is Ian's picture out of the instructions. So pretty straightforward. But what we're going to look at, these are the sections I've broken the presentation up into. What is it if you build it exactly as CAN VOUT? What flexibility do you get around power? What flexibility do you get around connectors, I/O, and firmware? Because as someone was saying before, with options comes complexity, but you can actually choose some rather simple firmware and do stuff a lot easier.
What's the size of the board? Is a matter of interest.
About, can you see my screen as well, or only the shared screen?
Only the shared screen.
Okay, I'll hopefully that'll pause the share. No, I've got to stop the share. Okay.
Okay.
So it's bigger than the CAN MIO board. A lot less dense. Yeah.
That's a CAN MIO.
Oh, that's the VOUT. The CAN MIO, yeah, I've got some of them around here.
This is just the board size I use, 50 by 100.
Yeah.
But to get all that stuff on, you need a reasonable size board.
You do.
100 by 75.
Yeah. Thank you, Kerry. So let's go back to there. Share that again. Share screen. That one. So CAN VOUT, the way the project's built, I disagree with the way they chose to build the project, but it's not hard to change it. So they built it with one 5-volt regulator for the whole project, and you can see it highlighted at the top there. Come on. It's got a driver chip down the bottom here that is driving the channels 1 to 8. And on these boards, 1 to 8 are the lower ones and 9 to 16 are the upper ones. And the driver puts positive outputs, where normally a MERG board, when you turn it on, turn an output on, its output is low. Channels 9 to 16 are up the top there, and they're inputs in the way this is configured. It comes with the CAN MIO universal firmware. There's been talk of them changing it to CAN MIO out. But if they do that, they won't be able to do the same thing. So they won't be able to get inputs on this board running outputs on the same board. As built, inputs 9 to 16 both generate events, and those events are consumed on this board to turn on the outputs down the bottom. So it's quite simple in the way it comes, and it's meant as a building block, a stepping stone to going and figuring out how CAN MIO universal works in more detail. These pictures, yeah, again, I've nicked these straight out of Ian's documentation, and he spent a lot of time on getting that documentation together, but the diagram here is pretty much straightforward as to what's going on. We can see the CAN chip down the bottom here. We can see the push button and the LED indicators there, the processor, the 8 IOs there for the first 8, and the 8 IOs up here for the second 8. And up here, U3 is the 7805 regulator that he's picked here. He hasn't put other regulators on the board. We'll look at the power options later in this presentation. pretty straightforward the way it's built and quite sparse. I would have liked to have seen them bring 12 volts out onto the outputs for the relays, but it's trivial to do that if you want to with the kit. We'll look at that later on. Again, this is, as Craig was talking about, the bits that aren't used on this project are grayed out. So you can see up the top here that U3 is the only regulator used, and he's taken down here it says the output for VO1. Now VO1 is the output for this down here. So you select which one you want. Do I want it coming from regulator 5? Do I want it coming from where? I want, in this case, he said I want the voltage of the processor, voltage of the PIC. For the second one, he's not even selected it there. So U3 is the PIC regulator voltage. So just by having U3 on the board, VP exists. So that link connects the processor voltage to the driver output power. So each of the outputs goes between 0 and 5 volts is all it does. Not real pretty, as Craig was talking about before. Relays kick up a bit of hash. The driver chip's got flyback diodes in there, so you're not going to get the voltage spikes coming out of the relays killing the driver chip. Reasonably straightforward. There's a resistor network up here, 8x1K, as we're used to seeing on the CAN servo boards and the like. So those 8 inputs have got the 8x1K there and 8x10K here for the pull-up resistors.
Big question, Greg.
Yeah.
You were saying that the driver chip is what normally is output is high normally. Is that right?
Yeah, they used a different one to the ones they used to use in the old CANAC 8s that used to go low. They've used one that goes high.
Okay, I was just looking at it. It's a pretty simple chip. That's a Toshiba chip.
Yeah.
Yeah, just a MOSFET.
Yeah, a D-channel MOSFET is what they say it is.
I think you can still plug the old chip in there if you wanted to.
You can, and in the selection of jumpers, you instead of you picking
yeah, that one.
low,
yeah.
you pick the highs.
Yep.
So it's straightforward. So here's a picture. It's a cutout of the circuit schematic in the documentation, and it was quite nice because it had all the voltage regulators across the bottom. So this is U3, which is 7805 on the board we looked at. It can have a 78L05 just to run the processor alone and nothing else. There's a provision for another 78 series regulator on there, and provision for an LM317, which is the one that's usually used for the servo boards. And that board can either be configured as 2 fixed resistors or 1 fixed resistor and a trim pot to adjust the voltage. So there's lots of options in there, and like I said, that confuses a pile of people. The other thing Ian did, and I quizzed him about this in some emails. When you look at some of these regulators, normally on MERG boards you find 100 microfarad on the front and you find a small 4.7 or 16 microfarad on the output of the regulator. When you look at the other regulators, he's done them the other way around. He's gone, I'll have a larger cap on the inside and a smaller one on the outside. His reasoning is, well, we've got a regulated supply anyhow, and if I put the larger cap on the input side, sorry, on the output side, I don't contribute as much to inrush current because the current through those regulators is limited. It's not like just having a whole pile of caps straight across the power rails. If the regulators are 1 amp regulators, they're limited to 1 amp as inrush current. So he did them the other way around on purpose. It'll work. It's unusual. You can do it the other way around if you want because there's plenty of room to put different caps in there if you want. So the 78005, as I said, it's for the processor only if you want to do that, and you'll see that in the bottom of the board later on. The second 7.8 regulator, if you were running, if you wanted 9 volts out for something, you can put a 7809 in there for your second regulator and pick that as the output power for one of the 2 blocks. And we know why you put the 317 in there. Ian's boards all have provision for the transient voltage suppression chip, and it's again under the board, so it's easy to put in there as an after if you want to. And the good news for us is these days with the 2562s being used as a standard CAN transceiver, they're not dying anywhere near as much as the old 2551s did. And the other bit of anecdotal evidence we're getting around the place is if you've got a CAN bus that's got 2551s on it, and you put a TBS in there somewhere on that bus, then the 2551s are no longer dying. So good news all around by putting them in your bus. Power flexibility. This is, I think, yeah, it's the first CAN V I built on one of Ian's newer generation boards. U3 is a 7805. I put a 317 regulator on this as well, and I set it to 5 volts out, so I didn't bother putting a trim pot in there to wind around the voltage, just what I wanted. I just went, right, I'll put 2 resistors in and get 5 volts out. And you select, the way it's done is, I'll go through the bullet points first and come back. U5, it's a 317. The tracks are actually big enough for 3 amps, and you can see this footprint for this diode here is big enough for a 5401 diode, so you can put in a 3 amp diode if you want, and you can put in the 350, which is the 3 amp version of the same regulator. The U3 and U6, he's got a footprint there so that if you put the switch mode regulators in, they don't hang off the side of the board as they do on the other boards that MERG have got. Funnily enough, I raised that with Pete and I think Mike Bolton years ago, and they went, no, I don't want to do it. But Ian's done it for these, which is nice. Let's just go through these. So you have jumpers or bridge selection. Put a bridge in to select the voltage sources. This here is the 12 volt line that comes up from the CAN connector. And you can choose the source for the voltage to supply to regulator 5 here. So there's a track runs up from this somewhere underneath on that one, I think, to go towards that regulator. It'll actually go through a diode. Yeah, it goes through that diode there. So it goes through there and then up to the regulator. So you can either power it from plus V, which is the second power supply input that they allow for on this board. So you can have the 12 volts coming in on the CAN connection, or you can bring in another supply and power it up here. So you pick which one you want. I spoke to Ian about this because one of the things that I found a little bit unusual was over here on these selectors for what do I want to give each bank. So V01 is for this bank here, and V02 is for the second bank. That's the other way around. Why does that show there? Yeah, there's actually a wire there, and that runs down to the second bank. So this one controls the second bank, and this one is for the power for the first bank. You can see the power coming off there to go to the first connector on the output. And you choose what you want. And just like Ian's stuff before, what do I want on this one? Well, on the output for the first one, I want the voltage of the processor. On the output of the second one, I wanted the output of U5. So what I did that for was, if I wanted to run outputs down here for relays and servos up here, then I would run the servos off this set of headers here, and I'd run my relays off the bottom one. Now I could easily pick 12 volts for my relays just by changing which one I pick up here. and take it to the 12 volt one. There is a little bit of a catch for young players in that, though, that I also spoke to Ian about. The 12 volt and the plus V that you see here, they are not polarity protected. So if you've got the voltage the wrong way around on those pins on the connectors, then and you use these, then you're at risk of putting reverse polarity on some of the components. I got around it on one of my boards quite easily by just going, okay, you know what, I'm going to use U6 for an input to, imagine I said I'm going to use U6 here. Well, I can put a regulator in there, or you know what, I can go, okay, I'm going to run U6 from the 12 volt coming in on the CBUS connector. And what you can do is put a link in here, or a diode standing up, and just put a link up here between the input and the output. And you get the same thing. All you've done is you said, right, I'm going to have diode protection, and do it. Well, imagine we put a diode in here between the 12 and that center pin just by standing it up in those holes. I put a link between the input and the output on the regulator. Boom. I get just shy of 12 volts as my input. Indeed, if I put a Schottky diode in, I'm so close to 12 volts I don't care. So that's what I did on one of them to make sure that I still had polarity protection on these boards. I've actually got his earlier generation boards that don't have the dual footprint, and the chips and some of the jumpers are numbered differently. So I have a bit more homework to do when I'm using these things. The pull-ups can be the pull-up or pull-down for these, just like we know from servos, where you say, right, I want to pull the line high or pull it low. You can either have it to be the output of the voltage that you've picked up here, or you can have the voltage of the processor, or you can pull it down to ground. The way he's done it is, if you join 3A across there, you get ground. If you want one a pull up, then you pick whether you want it to be VO2 or voltage of the processor there. So you only ever use the A or the B, you never use them both. That's the way to go bang. If you want to do bang, Craig, that's how to do bang. Join them both together.
I saw that, Greg.
Yeah, so pretty straightforward. Like I said, the 12 volt and plus V are not protected, but there's ways to use them that give you the protection. Connector flexibility. Well, I might just go back there. I know that's been whirlwind about what you've got for choices for power, and I'll just go back to the circuit diagram, I think. So back here you can see, if you do it the way Ian says, you can go in there and say, I do want another regulator, and you can pick the caps based straight off that circuit diagram to use on your board. Yep, that's the easy way to do it. If you want to use different caps, then make your mind up what you want and go straight ahead from there. The links that we saw for where is the power coming from for the regulators, you can see those represented here on this board. This red mark here, this is out of his CAN FLIMIO documentation, so that's why you see the red link in there. That's how he did it for that kit. The connector flexibility, I don't mind this either. Pete was talking about this, Pete and I were talking about this with respect to CAN FLIMIO the other day. You can put a 10-way 3.5 pluggable connector in there, which everybody's using as a standard now on the second generation boards. I'd actually like to see them have another mounting screw in here, because there's a fair bit of insertion force on a connector that's that big. And so you've got a rather long board, and you've got a couple of big connectors, and you're pushing them. But nobody's complained about breaking them yet. So that's where they're all going. And the idea is, if you're replacing a module in a layout and because it's failed, do you really want to plug in 16 connectors like this and get them all in the right order on the replacement board, or do you want to just plug in 2 connectors to get it going again? That's the logic that's behind it. This over here is a picture of one of, yeah, I think based on looking at those jumper numbers, this is a picture of one of my earlier revision boards. But you can see here's the connector pad for the 3.5 connection, and here's a connection pad, set of pads for 0.1. What Pete and I were talking about was there is no experimenter's kit that has the 3.5 connectors on them, and they'd be bloody dear, because those 3.5 connectors for a PCB board, the male ones, are quite expensive, and they're not as readily available. You can get them from AliExpress, but they're also not as cheap, because the female one for on the board is common, the one with the screw connectors for the cables is common, but a male one to plug into there on a PCB is not as common. So you can't get them from the likes of RS or Element 14.
I got groups of 20, the male and the female, from AliExpress, and I think they're about the 10-way, and they're about $8, $9 for 20.
Yeah, I got a big pile of them at somewhere. I was selling them out. Oatly or one of those mobs in Australia was selling a big fire sale of them, and I've got a bucket load of those things. I got some at AliExpress.
I got them from AliExpress as well, because I have 4 boards with a mobile layout, and so I use a lot of them, and they were cheap. Yeah,
if you're buying them at real price, they're often not cheap.
They're expensive.
Yeah. but yeah, go dig around AliExpress and you do find them. One of the things, as I was saying, there's no experimenter's kit that has the 10-way connection on there, but the old experimenter's kit used to have a female on the board and male connections on the experimenter's kit. What Pete has done, he's soldered in, he's basically put the 10-way 3.5 in, then he's offered up a right angle female one from below, and if you put the male and the female of the 3.5 in there together, because it reaches down lower again, then you can put the female 0.1 in there with an appropriate height to also sit there underneath. So if you're building one for on a demo board or whatever, where you want to plug those experimenter kits in, yeah, you can put the 0.1 swinging off the bottom of the board and the 3.5s on the top for when you want to use that board for real. So that's okay. You can see the servo style connectors that I've put on this board, so that I can play servos there. And that's about it for output connectors. There's no real need to talk about the input ones. You all know what's going on there. A 2-way 3.5 or a 4-way for the CBUS connector. IO flexibility is where it gets a lot more interesting, and interesting in the Chinese sense of the word. May you live in interesting times, because you get a lot of variation as to what you can do. The limits on granularity come pretty straight up as we're used to in these boards, where if I put a resistor pack in there, then I'm not going to be running relays from there. If I put a driver chip in there, I'm not going to be running inputs from there. That sort of granularity is obvious. But on the resistor pack one, you can do lots of other different things. I can do inputs, I can do servo outputs, I can do opto-coupled outputs, I can do LEDs. So I can do a lot of stuff with the resistor one. With the driver chips, I can do a few things as well. Relays and servos. Now, servos seems a bit odd, because we know the servo pulses, we know that normally MERG outputs go low when things are on, and that also means that the servo pulses are designed for, they're actually designed the other way around. They're designed for a negative output as their logic. What I mean by that is, when I put it through, if I put a servo pulse through here, it's actually got the wrong mark space. It's the wrong way around. I'm getting long pulses where I want short, and I'm getting short where I want long. So the CAN MIO universal software actually lets me do an inversion of the output. So I can say that the port is a servo. I can say the port is a servo port, but I can also invert the output. And then what happens is the pulses come out here the right way around. So out of the driver chip, I can run my relays and I can run servos if I want. So you get a lot of flexibility from the universal software. You get a little bit of flexibility when you start to play around a little bit. Some people are using the CAN MIO boards of various flavors, whether they've made their own, as Craig's doing at the moment, or whether they've just opted to put in links in some places in the boards rather than resistor packs and the like. Then they're using external boards that actually have the driver chips or whatever. Then you're out to, I can have however many I like running off a driver chip. I don't have to have 8, I could have 4. And I can run the other 4 outputs or the other 4 lines into inputs if I want. So you start to muck around with the granularity. I get why people do it. I'm not a real fan because, for instance, if I put servos out there, like the Easy Servo, as some people are doing out there, now I've got to configure my CAN MIO / Flim IO board, and I also have to go and configure the servo itself, the Easy Servo. So I've got more work to do. And unlike CBUS, where I can configure them all without having to go and connect to stuff, if I use the Easy Servos, I've got to go and plug cables into those to configure them. So I see swings and roundabouts. If you're doing it with input boards, yeah, for sure. But once you start doing it with outputs, I think it's starting to get a little bit silly. That said, if you were driving FETs to drive one CDU that you needed in one place, then fine. The servos, as I said, are easy to run from the driver chip. And if I only wanted 5 pull-ups on lines, I didn't want pull-ups on the other lines, well, I could put 4 pull-ups. I didn't want 8 pull-ups. I could put a 5-pin ResNet in there instead of the 9 and only put pull-ups on 4 of the lines. So you get a few choices as to what you do. And there's times when you don't want the pull-ups there. There are a couple of differences to CAN MIO that you kind of don't expect, because Flim IO is designed to run, the Flim IO boards are designed to run the CAN MIO firmware. There's more choices, power choices on Flim IO. We know the CAN MIO's got 2 power supplies. If you look at the CAN MIO daughter boards, you'll actually find that some of the daughter boards actually have another power input on it, so that you get that 3rd regulator capability. CAN MIO has daughter cards for different functions, but they're daughter cards that all do one thing. So it's all relays, or it's all tortoise control. So you sort of lose a little bit out on the story of CAN MIO Universal. Flim IO has pull-ups, well, the 9-pin ResNets after the 8x1K resistors. They're not before them. And on the CAN MIO, they're before them. But there's only 4 pull-ups. And in the CAN MIO Universal firmware, you get to say whether you want to use weak pull-ups in the chip for the other 4 lines. So there's a difference here. CAN MIO is doing it differently, and to that end, you're advised in the documentation to disable the internal pull-ups in the CAN MIO Universal firmware when you're using these boards. It's no big deal if it's there. You're gonna burn a few more milliamps. Who cares? You can see it on these 2 circuit diagrams. So this one here is the Flim IO E. We can see the 8x1K here, and if you had another 8x1K here, you see that the pull-ups are on the outside. Yeah. Over here is CAN MIO, and this could be the 8x1K, and there's the pull-ups for that. For the second lot, on the daughter card is the 8x1K, but they come after the presence of these pull-ups. Yeah? And if you've got the internal pull-ups running for these ones here, the weak pull-ups, then you can see that all our pull-ups are on the inside, not the outside. Works better if you're driving logic outputs, but it's not the way around you want it for logic inputs. It's not the best way to be. So there's a difference. It doesn't manifest in stuff, people going, oh, woe is me, the world is ending, but it's an anomaly. And if you know it's there, you know, okay, I'm using a Flim IO board, I turn these things off and away I go. So the CAN MIO universal firmware is brilliant, but it takes a bit to get your head around. So again, I would recommend go look at Dave's video. I suspect he's done a pretty good job this time of it. I had a go at it and I muffed it in the middle of it, and I was going to do it again, but I'll watch through Dave's to see if there's anything I wanted to add to it, and otherwise keep pointing people there. Sequences are the big thing I like in there. And of course, you can also consume its own events, which is kind of nice. CAN MIO out. If I run CAN MIO out on a board like this, I get 8 outputs, 8 inputs, and it's simple as. The configuration is trivial. It's just like drag and drop on any of the other boards. There is a slight gotcha in some of them that you can't use short events on the on the 8 inputs in a lot of the CAN MIO boards. CAN ACE-8C MIO turns that board into 16 inputs, and all you're doing is changing the driver chip for a set of pull-ups and the 8x1K resistor. So when you look at the board, they're really quite simple things to do. And I'm damn sure that if anyone said, oh, I want to do this, and they asked on the forum, people would come back pretty damn quick and say, this is all you have to do. Ian's documentation is reasonable on that stuff as well. He does show a hell of a lot of options. It sounds unfair to call it reasonable. He's done a lot of stuff in that documentation. He shows you how to drive relays, he shows you how to drive leads, he shows you how to configure inputs, all that sort of stuff is in there. But the documentation is very long, and I think a lot of people look at it and go, if this is how much I need to read to do it, it's too hard. But the thing to do is to, if you go put in your mind's eye the diagram we had earlier, we've got what do we want for voltage regulators coming in, what do we want for the first block of 8 channels, what do we want for the second block of 8 channels, and configure each of those as you go along, then life becomes partitioned and a lot easier. And you've got the CAN MIO servo software, 8 servos and 8 inputs. So again, life's pretty damn simple. As the CAN MIO was developed, some of the stuff that came along to run the extra 8 inputs turned up on the 2480 processors, and there used to be hacks for the old classic boards to add the extra 8 outputs or 8 inputs on those boards. It was a little bit messy because the pins being used were different. But some of the firmware that you find out there, you'll find that there is code out there for 2480 processors and 4 megahertz oscillators to do various jobs. Like there's definitely one for servo, there's definitely one for the MIO out. I think there's one for the 8C MIO. And when I first put my demo boards together for our group to play with, some of the boards were using the 4 megahertz and the 2480 processor because the 25K80 code wasn't ready yet. So it's certainly an interesting choice, and one of the choices you have if you want is to get your classic boards, rip the processor out and throw them in one of these boards and get a little bit more mileage out of them by getting the extra inputs. Now Craig and I differ on this. Craig goes, why would we run so dense? My choice is, hey, if I want to put in block control and then I want to come and do signals and all the rest of it, then all of a sudden the density of the channels that I need in that area gets higher. So I am starting to end up with more things in one place to control. That's as much as I put together. Now, I'm sorry, the ink's still wet on this. I put this presentation together today. So it's taken a little bit to get going, and I've been trying to deal with a young puppy in the place, and that's what buggered me. But I got there. So what I'd suggest to you is if you've got a CANV out or you're looking to get a CANV out kit, think about making it 12 volt as the output for the driver chips rather than 5 volts. The other board that is very similar in this is it's got a really weird name. CAN V4 BIP, I think it is. and it is the 2G version of the old CAN 5, but it's in the Flim IO series of boards. So Flim IO boards are all laid out the same for power, for where the connectors are, for how you configure the jumpers to the second bank of 8 connectors. Where they differ is in the driver chips that are required for the specific purpose. So tortoises, you need 2 driver chips to run the thing because you need the H bridge. So what you see on those is the documentation is going to be almost identically the same. It'll be a little bit different around here. Here's the drivers and here's the connections for that. So life's pretty straightforward. Once you get your head around one of the Flim IOs, your head's going to be in a good place for doing any of the Flim IO boards. Talking to Pete Brownlow, his preference is obviously the CAN MIOs. He designed them, he built them the way he likes. He likes stacked boards. He likes, here's my processor, here's my primary function coming out of the first 8 ports on there, and my secondary function, I put a daughter card in there to do the secondary function. That's the way he likes it. For mere mortals in MERG, I think the Flim IOs are going to be a more common choice because they're easier to build.